Imagine a world where the skies rain acid, the air crushes you with the weight of 1,000 oceans, and the ground glows with rivers of molten metal. This isn't some distant sci-fi nightmare, it's Venus, our closest planetary neighbor, a place so hostile it's earned the nickname Earth's evil twin. But here's the thing, behind its hellish facade lies a treasure trove of secrets that have left scientists scratching their heads for decades. From its bizarre, backward spin to its mysterious glowing peaks, Venus is hiding puzzles that defy everything we think we know about planets. What if I told you that this world, often overshadowed by Mars and its search for life, holds some of the most jaw-dropping anomalies in our solar system? Picture a planet where a single day lasts longer than its entire year, where winds whip faster than hurricanes yet the surface barely moves, and where ancient volcanoes might still be whispering with activity. Venus doesn't just challenge our understanding, it downright mocks it. And the deeper we look, the stranger it gets. That's why today we're diving into 25 of the most mind-bending mysteries of Venus and enigmas that even the brightest minds haven't cracked. From its suffocating, super-rotating atmosphere to the eerie snow that caps its mountains, each one of these riddles pulls back the curtain on a world that feels more like a cosmic riddle than a planet. So buckle up, because by the time we're done, you'll see Venus in a whole new light, and you might just question everything you thought you knew about our solar system. Venus doesn't just have a greenhouse effect. It's the solar system's ultimate cautionary tale of what happens when climate spirals out of control. While Earth's atmosphere keeps us comfortably warm, Venus took that idea and cranked it up to a nightmarish extreme. Its air isn't just thick with carbon dioxide, it's 96% carbon dioxide, a suffocating blanket that traps heat like a cosmic pressure cooker. The result, surface temperatures soaring past 880 degrees Fahrenheit, hot enough to liquefy lead and turn zinc into puddles. Here's where it gets really strange. Scientists believe Venus once had oceans, maybe even conditions similar to early Earth. But somewhere along the way, something triggered a catastrophic domino effect. As the planet warmed, water evaporated, feeding more greenhouse gases into the atmosphere. The gases trapped more heat, which evaporated more water until Venus crossed a threshold where the entire climate system went into overdrive. What we see today is the aftermath, a planetary furnace where even the nights are scorching and the very rocks glow red under the oppressive sky. Yet the biggest puzzle isn't just how it happened, it's why Venus took such a radically different path than Earth. Both planets formed from similar materials at roughly the same distance from the Sun. So what tipped the scales? Was it a slower rotation that doomed Venus to bake under endless sunlight? Ancient volcanic eruptions that pumped the atmosphere full of gases? Or some forgotten cosmic event that set this runaway process in motion? Even more unsettling, Earth's climate shows eerie parallels on a smaller scale. Our own carbon dioxide levels are rising, and while we'll never become Venus, studying its hellish landscape gives us vital clues about the delicate balance that keeps a planet habitable. Every probe we send into those toxic clouds brings back data that feels like reading the final chapters of a cautionary tale written in atmospheric chemistry. Venus isn't just a mystery, it's a mirror, showing us just how precarious the Goldilocks zone of planetary comfort really is. High above Venus's scorching surface, where the air is still thick enough to crush a submarine, something strange paints the clouds. Dark, streaky patterns swirl through the planet's upper atmosphere, visible only in ultraviolet light. These eerie markings come from a mysterious substance scientists call the unknown ultraviolet absorber, a chemical or particle that hungrily soaks up UV radiation like cosmic ink. For decades, this enigma has defied explanation, hiding in plain sight while transforming Venus's clouds into a canvas of shadowy brushstrokes. Theories abound, but none fully crack the case. Some point to sulfur compounds. Venus's atmosphere is swimming with them, and certain sulfur-based molecules could theoretically absorb UV light. Yet lab experiments struggle to replicate the exact pattern seen in Venus's clouds. Others suggest iron chloride, a compound that could form from volcanic gases reacting high in the atmosphere. But here's the twist: the absorber's behavior changes over time, waxing and waning in ways that don't neatly match simple chemistry. Then there's the wild card. Could this be a sign of life? It sounds like science fiction, but some researchers speculate that microbial organisms, if they existed in Venus's temperate cloud layers, might produce pigments as a shield against solar radiation. On Earth, extremophiles thrive in acidic environments, and certain bacteria even absorb UV light in ways that resemble the Venusian puzzle. Of course, extraordinary claims require extraordinary evidence, and so far, no spacecraft has scooped up a smoking gun. What makes this mystery so tantalizing is how it ties into Venus's greatest riddles. The absorber isn't just a passive stain. It may play a role in the planet's frenetic weather, influencing how sunlight heats the atmosphere and fuels those supersonic winds. Every probe we've sent has added new clues but no definitive answers, leaving us with a cosmic whodunit written in ultraviolet shadows. Until we sink another mission into those toxic skies, the absorber remains one of Venus's most persistent secrets. A reminder that even in the most inhospitable places, the universe keeps its cards close. If you stood on the surface of Venus, you'd witness something impossible on Earth, a sky that races around the planet while the ground barely moves at all. While Venus itself takes 243 Earth days to complete one sluggish rotation, its upper atmosphere streaks around the planet in just 4 days, 60 times faster than the surface below. This dizzying mismatch, called super-rotation, turns the planet into a giant cosmic blender, with winds howling at hurricane speeds yet leaving the landscape eerily still. No other world in our solar system behaves this way, and the mechanics behind it have left physicists both fascinated and frustrated for decades. One leading theory points to thermal tides, massive pressure waves generated by the sun's brutal heating of Venus's dayside. As sunlight fries the thick atmosphere, gases expand violently, creating bulges that travel around the planet. These tides could act like invisible hands, pushing the atmosphere forward and accelerating it to incredible speeds. But here's the catch: computer simulations can't quite replicate the extreme velocity we observe. The numbers suggest thermal tides should contribute to super-rotation, but not enough to explain the full 60-fold difference. Something else is clearly at play. Another puzzle lies in how momentum gets transferred upward from the surface. Near the ground, Venus's winds are sluggish, barely nudging the planet's rotation. Yet somehow, energy gets pumped into the upper atmosphere, like a silent engine revving the clouds to supersonic speeds. Some researchers suspect turbulence or waves in the lower atmosphere might act as a conveyor belt, ferrying momentum upward, but the exact mechanism remains elusive. Then there's the wild card: Venus's lack of a magnetic field. Without this protective shield, solar wind particles slam into the upper atmosphere, potentially stirring it like a spoon in a cup of coffee. Could this interaction help sustain those relentless winds? Or does the answer lie in the planet's slow rotation itself, creating a peculiar balance of forces we haven't yet untangled? Every model scientists build seems to miss a piece of the puzzle. Even Earth's own jet streams, which pale in comparison to Venus's atmospheric sprint, offer few clues. This isn't just an academic curiosity. Understanding super-rotation could rewrite how we think about planetary weather systems, especially on exoplanets with similar conditions. Until we send more probes into those corrosive clouds, Venus's whirling atmosphere remains one of the solar system's most captivating fluid dynamics experiments, a reminder that even the simplest question, why does the wind blow, can defy explanation on other worlds. Venus wasn't always a parched wasteland. Billions of years ago, it might have sparkled with vast oceans, perhaps even shallow seas lapping against rocky shores under a hazy sky. But today, if you searched every scorching valley and mountaintop, you'd struggle to find even a single molecule of liquid water. The question isn't just where it went, but why Venus, so similar to Earth in size and origin, became a desert while our planet remained a blue oasis. The culprit lies in a perfect storm of cosmic bad luck. Unlike Earth, Venus lacked a magnetic field to shield it from the sun's relentless solar wind, a stream of charged particles that acts like a sandblaster on atmospheres. Over eons, this wind hammered Venus's upper layers, stripping away lighter elements, including hydrogen. And here's the critical part: hydrogen is half of water's recipe. Lose enough of it, and oceans literally evaporate into space, molecule by molecule, leaving behind a bone-dry world. But solar wind alone doesn't explain the scale of the disaster. Venus's proximity to the sun meant it received far more ultraviolet radiation, which can break water vapor apart into hydrogen and oxygen high in the atmosphere. The hydrogen escaped, while the oxygen either bonded with rocks or vanished into chemical reactions, leaving no trace of its aquatic past. Meanwhile, Earth's stronger magnetic field deflected the worst of the solar wind, and our cooler temperatures kept water safely pooled on the surface rather than boiling into a runaway greenhouse effect. Yet the mystery deepens when we examine the speed of this disaster. Some models suggest Venus could have lost its water in as little as 100 million years, a geological blink of an eye. If true, it implies a sudden, violent shift rather than a slow decline. Was there a tipping point, some final volcanic eruption or atmospheric change that sealed its fate? The irony is haunting. Venus may have been as habitable as Earth once, until a chain of small differences, slower rotation, slightly closer orbit cascaded into catastrophe. Studying its desiccated surface isn't just about solving a planetary whodunit. It's a warning about how delicate the balance of water and atmosphere really is. Every mission to Venus brings us closer to understanding not just our sibling planet's tragedy, but the fragile line between a living world and a lifeless one. Venus's volcanic past is written across its surface in vast plains of hardened lava, towering shield volcanoes and strange pancake-shaped domes, more volcanoes than any other planet in our solar system. But here's the burning question: are any of them still erupting today? The answer is maddeningly unclear, buried under layers of conflicting evidence and that impenetrable atmosphere. On one hand, Venus's lack of plate tectonics should mean its volcanic activity has simmered down over billions of years. On the other, fresh lava flows spotted by spacecraft suggest the planet might still be belching molten rock into those toxic skies. We just can't catch it in the act. Take the case of Idun Mons, a massive volcano standing 5 miles high. Infrared scans revealed strange hotspots along its slopes, glowing as if lava had cooled there geologically yesterday, or maybe even this morning. Then there's the lava flow near Mons, stretching over 20 miles and showing mineral signatures that haven't had time to weather under Venus's corrosive atmosphere. These aren't ancient relics, they're practically steaming. Yet despite these smoking guns, no probe has ever captured an actual eruption, leaving scientists arguing over whether Venus is volcanically active or just really, really good at faking it. Part of the problem is Venus's thick, cloudy shroud, which blocks most telescopes from seeing the surface in real time. Even radar-equipped orbiters like Magellan could only map the terrain in snapshots spaced years apart, hardly enough to catch something as fleeting as an eruption. And let's not forget the surface conditions. With temperatures hot enough to melt lead and pressures akin to the deep ocean, any lander we send fries or crushes within hours, leaving us with barely a glimpse of geological activity. But here's where it gets intriguing. Venus's atmosphere holds chemical fingerprint spikes of sulfur dioxide that wax and wane mysteriously like smoke from unseen fires. Some researchers argue these fluctuations hint at ongoing eruptions, pumping fresh gas into the skies. Others counter that the planet's violent winds could simply be shuffling old sulfur around. Without direct evidence, it's a debate as hazy as Venus's own clouds. The stakes are higher than they seem. If Venus is still volcanically active, it challenges everything we know about how rocky planets age. Earth's eruptions are fueled by shifting tectonic plates, but Venus has no such system, so what's driving its fires? Could it be residual heat from its violent youth, or some exotic form of mantle convection we haven't discovered yet? Every unexplained hotspot and unweathered lava flow is a clue, whispering that Venus might not be the geologically dead world we once assumed. Until we peer through those clouds for good, the planet's volcanic heartbeat, or lack thereof, remains one of its most tantalizing secrets. Among Venus's scorched plains and volcanic giants, the tesserae stand out like ancient ruins, jumbled highlands crisscrossed with fractures so complex they resemble shattered glass frozen in stone. These sprawling plateaus, some as large as Australia, rise miles above the surrounding terrain, their ridged surfaces etched with grooves running in chaotic, intersecting patterns. Unlike anything on Earth, these formations whisper tantalizing hints that Venus might have a geological story far stranger than we ever imagined. The leading theory suggests these fractured highlands could be Venus's version of continents not built from plate tectonics like ours, but forged through some other violent process. One idea points to massive bursts of lava welling up from below, stretching and cracking the surface like hardening paint on a balloon. Another proposes that the planet's crust, under relentless heat and pressure, simply buckled and warped over time, folding in on itself like a crumpled sheet of metal. But here's the twist: some tesserae show layers, like pages in a book, suggesting they might be remnants of repeated volcanic floods or even ancient crustal collisions. Then there's the mystery of their age. Unlike Earth, where erosion and shifting plates constantly recycle the surface, Venus's lack of water and stagnant crust means its tesserae could be staggeringly old, perhaps relics from a time when the planet still had a mobile, dynamic shell. If so, they're time capsules preserving clues about Venus's lost geological youth. Yet recent radar scans reveal something even more puzzling. Some regions appear younger than expected, hinting that whatever shaped them might still be at work today. What makes these formations so mesmerizing is how they defy easy classification. On Earth, mountain ranges and plateaus usually trace their origins to familiar forces, colliding continents or erupting hotspots. But Venus plays by different rules. Without plate tectonics, the tesserae seem to scream that we're missing a fundamental piece of the puzzle. Could they be the scars of a long-dead tectonic system, frozen in place when the planet's core cooled, or signs of a completely alien process, one where lava, heat, and pressure dance in ways we've never seen? Every new mission to Venus inches us closer to answers. The upcoming Veritas orbiter, equipped with cutting-edge radar, aims to map these fractured highlands in unprecedented detail, peeling back the layers of their history like a planetary archaeologist. Until then, the tesserae remain one of Venus's most stubborn enigmas, a labyrinth of stone holding secrets about how rocky worlds evolve when stripped of the forces we take for granted on Earth. Venus's thick, churning clouds might be hiding one of the solar system's most electrifying debates. Does lightning actually strike there? For decades, scientists have gathered tantalizing but contradictory clues, turning what should be a simple yes or no question into a full-blown cosmic whodunit. The case for lightning began with Soviet probes in the 1970s and 80s. Venera missions recorded bursts of radio waves and electromagnetic pulses strikingly similar to terrestrial lightning, while later orbiters like Pioneer Venus and the European Space Agency's Venus Express picked up more of these crackling signals. The evidence seemed solid. Venus, despite its alien atmosphere, was flashing with electrical storms just like Earth. But then came the plot twist. More recent missions, like Japan's Akatsuki orbiter, failed to detect any definitive lightning at all. Not a single bolt. This glaring discrepancy left researchers scrambling. Were the earlier detections false positives, or was Venus's lightning somehow vanishing? The stakes are higher than they seem. Lightning isn't just a light show. It can fundamentally alter a planet's chemistry, breaking apart molecules and sparking reactions that might even influence the possibility of life. One explanation points to Venus's bizarre weather. Unlike Earth, where lightning forms in water-rich thunderclouds, Venus's storms rage in sulfuric acid vapors. Electrical discharges in this corrosive environment might produce weaker, rarer, or fundamentally different signals that modern instruments struggle to catch. Or perhaps the earlier probes were misled by other phenomena, solar wind particles slamming into the atmosphere, or even interference from Venus's own ionosphere. Then there's the tantalizing possibility that lightning comes and goes in cycles. Venus's atmosphere is a dynamic, chaotic system, with storms that could wax and wane over decades. If true, it would mean the planet has storm seasons we've only glimpsed in fragments. The truth might lie in the clouds themselves. Some researchers suspect lightning could be clustered in specific, hard-to-study layers, hiding from our probes like a game of atmospheric hide and seek. Without a dedicated mission designed to hunt these discharges, the mystery endures. What's at stake isn't just solving a planetary puzzle, it's rewriting our understanding of how atmospheres behave under extreme conditions. If lightning exists on Venus, it challenges everything we know about how electrical storms form. If it doesn't, we have to explain why so many probes thought they saw it. Either way, the answer will illuminate one of the most misunderstood worlds in our solar system, proving once again that Venus refuses to play by Earth's rules. Even in its darkest hours, Venus refuses to be completely invisible. On the planet's night side, where sunlight should be nothing but a memory, a faint, ghostly glow lingers, an eerie radiance that defies straightforward explanation. This phenomenon, known as ashen light or bright nights, has puzzled astronomers for centuries, appearing like a spectral echo of daylight stubbornly clinging to the shadows. Imagine standing on Venus's scorching surface beneath a pitch-black sky, only to see the rocks around you dimly illuminated by an unknown source. It's not sunlight, not volcanic fire, just a mysterious, diffuse luminescence seeping from the very air itself. So where does this glow come from? One leading theory points to atomic oxygen high in the atmosphere. During the day, ultraviolet radiation from the sun splits carbon dioxide molecules, releasing lone oxygen atoms. When these atoms drift to the night side and collide, they recombine into molecular oxygen, releasing energy in the form of a soft glow, similar to the auroras on Earth but spread across the entire sky. This process, called recombination emission, could paint Venus's nights with an otherworldly sheen. But not everyone's convinced. Some researchers argue the glow is too widespread and inconsistent to be explained by oxygen alone. Could electrical activity be at play? Venus's thick clouds are infamous for their electrostatic potential, and fleeting bursts of electrical discharges, whether true lightning or some exotic form of plasma interaction, might contribute to the illumination. There's even speculation that the planet's relentless winds could be generating a weak planet-wide electrical current, lighting up the atmosphere like a faint neon sign. Here's where it gets stranger. Historical observations suggest the glow isn't constant. It flickers, brightens, and occasionally vanishes altogether. Some early astronomers, like Giovanni Cassini in the 17th century, reported seeing the phenomenon clearly, while others using more advanced instruments found nothing at all. This inconsistency hints that whatever's causing the glow might be tied to Venus's chaotic weather patterns, surging and fading with the planet's mysterious atmospheric tides. The real enigma is why we still don't have a definitive answer. Modern spacecraft like Venus Express and Akatsuki have scanned the night side for emissions, but the data remains inconclusive. caught between tantalizing hints and frustrating gaps. What we're left with is a celestial detective story where the clues keep shifting. If the glow is from oxygen, why doesn't it match our models perfectly? If it's electrical, why can't we catch it in the act? Until another mission brave enough to face Venus's hellish conditions returns with more clues, the bright nights remain one of the planet's most poetic mysteries, a reminder that even in the darkest corners of our solar system, light finds a way to defy expectations. And that's the beauty of Venus. Just when you think you've got it figured out, it gleams at you from the shadows, daring you to look closer. Earth's magnetic field shields us from solar radiation, guiding compasses and protecting life. But Venus, our planetary twin, spins silently without this invisible armor. Despite having an iron-rich core similar in size to Earth's, Venus generates no global magnetic field, leaving its atmosphere exposed to the solar wind's relentless stripping. This absence is one of the planet's deepest contradictions. How can two worlds with such similar building blocks end up so magnetically different? The answer might lie in speed, or rather, Venus's lack of it. Our planet's rapid rotation, completing a full spin every 24 hours, churns its molten outer core like a dynamo, generating Earth's protective magnetic shield. Venus, by contrast, takes 243 Earth days to complete one sluggish turn. Some scientists argue this glacial pace simply can't whip the core into the same electrically conductive frenzy. Without that churning motion, the theory goes, Venus's iron core might be as still as a stagnant pond, incapable of producing a planet-wide magnetic field. But rotation isn't the only suspect. Venus's core might lack the necessary heat flow to drive convection, the rising and sinking of molten material that powers magnetic dynamos. Earth's core stays hot partly due to radioactive decay and the crystallization of its inner core, which releases latent heat as it solidifies. If Venus's core cooled too quickly or never developed a solid inner core, it could have shut down its dynamo billions of years ago. Others speculate that Venus's core might even be entirely molten, with no solid inner core at all, robbing it of the temperature contrasts needed to stir the metallic ocean. Then there's the wildcard possibility. Venus once had a magnetic field, only to lose it in a catastrophic resurfacing event. Some models suggest the planet's mantle might have grown so hot and sluggish that it effectively locked the core, preventing convection. Imagine a pot of soup left too long on the stove without stirring. The heat distributes unevenly and eventually the system stalls. What makes this mystery so urgent is its ripple effect. No magnetic field means no protection from solar wind, which could explain why Venus lost its water and became the hostile world we see today. Every mission that probes the planet's interior, like NASA's upcoming Veritas, which will map gravitational anomalies, brings us closer to solving this planetary whodunit. Until then, Venus's silent core remains a haunting reminder that even twins can grow up under wildly different skies. Scattered across Venus like colossal fingerprints pressed into molten rock, coronae stand as some of the most perplexing geological features in the solar system. These bizarre, ring-shaped structures, some stretching over 1,000 miles wide, aren't just oversized volcanoes. They're planetary enigmas with raised rims, fractured interiors, and central depressions that look like the aftermath of a cosmic thumb pressing down on soft clay. Picture a giant bullseye etched into the landscape, but instead of arrows, these circles tell a story of fire, collapse, and forces we're still struggling to understand. The leading theory suggests coronae are born from mantle plumes, blobs of superheated rock rising from deep within Venus's interior. As these plumes reach the base of the crust, they spread like pancake batter, lifting the surface into a dome. But here's where things get weird. Unlike Earth's hotspot volcanoes, which erupt and build mountains over time, Venus's coronae often show signs of dramatic collapse. The domes crack, sag, and sometimes even crumble inward, leaving behind those distinctive rings. It's as if the planet can't decide whether to push the land up or suck it back down, a geological tug-of-war frozen in time. Yet not all coronae fit this neat explanation. Some lack clear plume signatures, while others sit in clusters that defy simple upwelling models. This has led scientists to propose a wild alternative: gravitational relaxation. Venus's crust, under relentless heat and pressure, might behave less like solid rock and more like slow-moving putty. Over millions of years, thick layers of lava could simply slump under their own weight, creating those circular depressions without any plume activity at all. Imagine pouring syrup onto a tilted plate eventually. It spreads and settles into a rounded shape, not because of forces below, but due to its own weight and viscosity. Then there's the outlier possibility. Coronae could be relics of a long-dead tectonic system. On Earth, continents shift and collide, recycling crust in a never-ending dance. Venus, lacking plate tectonics, might have once had a different form of crustal recycling, one where vast blobs of crust sank back into the mantle in discrete circular zones. The coronae we see today could be the scars of these ancient sinking plates, like ghostly imprints of a process that vanished billions of years ago. What makes coronae truly mesmerizing is their sheer variety. Some appear pristine with crisp ridges and well-defined rings, while others are so weathered they're barely recognizable. The largest, like Artemis corona, could swallow entire countries, while smaller ones might span mere dozens of miles. This diversity hints that multiple processes could be at work. Perhaps plumes create some, while collapse or crustal sinking forms others. Or maybe coronae evolved through stages, starting as domes before collapsing into rings over eons. The mystery isn't just academic. Understanding coronae could rewrite how we think about planetary interiors, especially on worlds where plate tectonics doesn't operate. They might even hold clues about Venus's lost water. Some researchers speculate that ancient coronae could have channeled heat and gases, accelerating the planet's climatic doom. Every new radar map peels back another layer of their secrets, but until we land a probe amid those fractured ridges, these gargantuan rings will keep taunting us with questions written in fire and stone. Venus, ever the cosmic riddler, ensures that even its geology refuses to follow the rules. High above Venus's south pole, a monstrous whirlpool of gas churns endlessly, a tempest so vast it could swallow Earth's largest hurricanes without a trace. Dubbed the Dragon Storm for its serpentine shape and relentless fury, this swirling vortex is one of the planet's most jaw-dropping atmospheric anomalies, a perpetual maelstrom locked in place where no storm should logically survive. Unlike Earth's fleeting cyclones, which dissipate within days, this beast has raged for decades, possibly centuries, spinning in defiance of every model scientists throw at it. What makes the Dragon Storm so baffling is how it mirrors Jupiter's Great Red Spot. A giant, stable vortex anchored to a pole yet exists in an environment utterly unlike the gas giants. Jupiter's storms feed off deep atmospheric currents and rapid rotation, but Venus spins at a crawl with no obvious energy source to sustain such a cyclone. Even stranger, the storm isn't just sitting there. It morphs constantly, changing shape from hour to hour, sometimes splitting into twin vortices before merging back into one. It's as if the planet's atmosphere is caught in a chaotic dance with the Dragon Storm as its unpredictable lead. The secret might lie in Venus's super-rotating winds. While the planet itself barely moves, its upper atmosphere screams around it at hurricane speeds, creating sheer forces that could twist gas into these monstrous vortices. Some scientists suspect the polar vortex is a side effect of this mismatch, a kind of atmospheric drain, where fast-moving winds collide and spiral downward, like water circling a bathtub's plug. But here's the catch: simulations can't replicate the storm's stability. On paper, such vortices should tear themselves apart or drift away, yet the Dragon Storm clings to the pole with eerie precision. Then there's the wild card of Venus's polar dipole. Unlike Earth's single polar vortex, Venus often sports two swirling eyes side by side, a phenomenon seen nowhere else in the solar system. These twin storms might be linked to atmospheric waves pulsing from the equator, or perhaps some hidden instability in the planet's jet streams. But every time researchers think they've cracked the code, the dragon storm throws a new curveball, like the time it suddenly stretched into a bizarre, elongated tendril spanning thousands of miles, a shape no model predicted. The stakes go beyond Venus. Understanding how such vortices form and persist could reshape our knowledge of atmospheric physics, especially on exoplanets with similarly hostile climates. If a slow-spinning world like Venus can birth a permanent polar storm, what other impossible weather might lurk out there? Until we send more probes into those acid-laced clouds, the dragon storm remains a swirling enigma, a reminder that even the most hellish corners of our solar system still hold surprises capable of rewriting the rules. In 2020, a bombshell discovery sent shockwaves through the scientific community. Astronomers detected phosphine gas in Venus's clouds, a compound that on Earth is almost exclusively tied to biological activity. The announcement ignited immediate excitement. Could this be the first whiff of alien life, floating 50 kilometers above the planet's scorching surface in a temperate, habitable zone? Phosphine, a molecule made of one phosphorus atom and 3 hydrogen atoms, stubbornly resists natural formation in Venus's harsh environment. Without life, how could it exist there at all? The initial detection came from the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile, which spotted a telltale dip in Venus's spectrum at the exact wavelength phosphine absorbs. The signal pointed to concentrations of about 20 parts per billion, small but impossible to ignore. Researchers ran countless models testing volcanic eruptions, meteorite impacts, even lightning-induced chemistry, but nothing could explain the abundance. That left one electrifying possibility: microbial life drifting in those acidic droplets, producing phosphine just as Earth's bacteria do in oxygen-free environments like swamps and animal guts. But the euphoria was short-lived. Almost instantly, other teams challenged the findings. Some argued the data had been misinterpreted. Perhaps the telescopes had actually detected sulfur dioxide, a common Venusian gas with a similar spectral signature. Others pointed to calibration errors or noise in the instruments. The debate grew so heated it spilled into headlines, with scientists divided between cautious optimism and outright skepticism. Even the original team admitted the detection was on the knife's edge of their equipment's capabilities, leaving room for doubt. Then came the rebuttals. Follow-up studies using different telescopes failed to replicate the phosphine signal at all. Critics suggested the initial analysis might have overlooked Venus's complex atmospheric chemistry, where unknown reactions could mimic phosphine's fingerprint. Even if the gas was present, they argued, it could stem from exotic geologic processes we haven't yet discovered. After all, Venus has already defied expectations with its volcanic quirks and atmospheric oddities. Yet the mystery refuses to die. In 2023, a reanalysis of old data from NASA's Pioneer Venus probe hinted at traces of phosphine buried in decades-old readings, reigniting the debate. Could both modern and vintage instruments have glimpsed the same elusive gas? Or is this a case of scientific pareidolia, seeing patterns where none exist? The heart of the controversy lies in Venus itself. Its atmosphere is a chaotic, corrosive labyrinth filled with chemical interactions we've barely begun to map. Without a dedicated mission to sample those clouds directly, the phosphine question lingers like a tantalizing mirage. Some propose sending balloon-borne labs to analyze the air in real time. Others advocate drills to hunt for microbial remnants in the planet's high-altitude haze. What makes this debate so captivating isn't just the hunt for life. It's the reminder of how much we still don't understand about our closest planetary neighbor. Venus, ever the trickster, dangles clues just out of reach, daring us to look closer. Whether phosphine turns out to be a biosignature or just another atmospheric illusion, one thing's certain: the universe loves a good mystery, and Venus is more than happy to oblige. Venus should be covered in scars, with no plate tectonics to erase them and an atmosphere too thick to burn up small impactors. Its surface ought to bear the marks of every cosmic collision over billions of years, yet when we map it, the planet reveals a shocking lack of craters. Compared to the battered face of Mercury or even our own moon, Venus looks almost pristine. This glaring discrepancy, known as the crater paradox, suggests something extraordinary happened in the planet's past, something that wiped its slate clean on a planetary scale. The leading theory is catastrophic resurfacing, a global volcanic apocalypse that drowned nearly every inch of Venus in fresh lava between 300 and 500 million years ago. Imagine flood basalts like the Deccan Traps on Earth, but multiplied to cover the entire planet, burying ancient craters under miles of molten rock. Radar maps from NASA, a Magellan mission, seem to support this. They show a surface dotted with relatively young volcanic features, but shockingly few older than 500 million years. It's as if Venus hit a cosmic reset button, erasing most of its geological memory in one fiery spasm. But here's where the paradox deepens. If resurfacing was truly global, why do a handful of regions, like the rugged tesserae, appear to have survived unscathed? These fractured highlands might be remnants of pre-cataclysm terrain, islands of antiquity floating in a sea of fresh lava. Some researchers argue this selective preservation hints at a more nuanced process, where resurfacing came in waves rather than a single event. Picture a planet slowly cooking itself from the inside out, with massive mantle plumes triggering episodic eruptions over eons, each one burying parts of the past but never all at once. Then there's the wild card: could Venus's thick atmosphere be skewing the crater count? While it can't stop large impacts, the planet's soupy air acts like a natural shield against smaller projectiles, vaporizing them before they reach the surface. Some models suggest up to 90% of potential crater-forming objects might disintegrate mid-flight, leaving only the largest scars behind. Yet, even accounting for this filter, the numbers don't quite add up. Venus still has fewer big craters than it should. The most unsettling possibility is that we're reading the evidence wrong. What if the resurfacing wasn't a one-time catastrophe but the tail end of an ongoing process? Recent studies of volcanic hotspots and unweathered lava flows hint that Venus might still be geologically active today, just at a slower pace. If so, the lack of craters could reflect a steady, planet-wide renewal, like a giant conveyor belt of lava gradually recycling the surface. Solving this riddle isn't just about Venus. It could redefine how we understand planetary evolution. Earth's surface constantly refreshes through tectonics, while dead worlds like Mars preserve their scars indefinitely. Venus offers a third path, a world that might remake itself in sudden, violent bursts. Every new mission, from Verita's high-resolution radar to DAVINCI atmospheric probes, peels back another layer of this enigma. Until then, the crater paradox stands as one of the planet's most tantalizing mysteries, a cosmic whodunit written in lava and shadows. Mont Mons doesn't just tower over Venus's landscape, it dwarfs Everest by over a mile, a colossal peak of fire stretching nearly 5 miles into the toxic sky. This isn't just a volcano, it's a geological titan, one of many shield volcanoes on Venus that make Earth's mightiest mountains look like foothills. But here's the puzzle: how did these monsters grow so immense on a planet without plate tectonics, the very process that fuels Earth's volcanic activity? The answer lies in Venus's peculiar, almost addictive relationship with lava, a planet that doesn't just erupt but drowns itself in molten rock on a scale we can barely comprehend. On Earth, volcanoes like Mauna Loa or Kilauea are born from hotspots or tectonic collisions, where crustal plates drift over magma chambers, creating chains of relatively modest peaks. Venus, though, plays by different rules. With no shifting plates to divert its magma, the planet's eruptions are free to build upward in the same spot for millions, possibly billions of years. Imagine a single, unrelenting fire hose of lava pouring onto the surface, layer after layer, century after century, until the mountain it creates becomes a sprawling, flattened giant. That's the secret of Mont Mons and its kin. They're not just volcanoes, but monuments to geological patience, sculpted by eruptions that never had to move an inch. Yet size isn't the only oddity. Venusian lava is far runnier than Earth's, flowing like syrup across vast distances before cooling. This low-viscosity basalt doesn't pile up into steep cones like Mount Fuji. Instead, it oozes outward, creating those characteristic shield shapes with gentle slopes that stretch for hundreds of miles. The result, volcanoes so wide you could hike for days across their flanks without realizing you're climbing at all. But the real mystery isn't how these volcanoes formed, it's why they didn't collapse under their own weight. On Earth, massive volcanoes eventually sag into the mantle, their sheer bulk triggering gravitational spreading that limits their growth. Venus, though, seems immune to this rule. Some researchers suspect the planet's scorching surface temperature, hot enough to soften rock, might act like a supportive cushion, preventing the crust from buckling. Others propose that Venus's stagnant lid of crust is simply thicker and stronger, locking these lava behemoths in place like fly traps in amber. Then there's the haunting question of time. Earth's volcanoes sputter and die as plates carry them away from their magma sources. Venus's, though, might have had uninterrupted access to magma for eons, fed by plumes rising from a core that never stopped churning. Could Mont Mons still be active today, its fiery roots smoldering beneath that fractured surface? Radar images show what might be fresh lava flows near its base, but without a lander brave enough to endure the heat, we're left guessing. What makes these volcanoes so mesmerizing isn't just their scale, it's what they reveal about the chaos of planetary evolution. Venus took the same ingredients as Earth and baked them into something entirely alien. A world where fire builds mountains that defy physics, where eruptions don't just shape the land but rewrite the rules. Every new radar scan peels back another layer of their secrets, but until we touch that lava-scarred ground ourselves, these peaks will stand as silent sentinels, guarding the mysteries of a planet that refused to follow the script. Venus's atmosphere isn't just thick. It's a bubbling cauldron of sulfur, a hellish brew where sulfuric acid clouds drift and sulfur dioxide levels swing wildly without warning. This isn't just random chemistry, it's a planetary scale puzzle that could hold the key to understanding whether Venus is still volcanically alive. The numbers alone are baffling. In just a few decades, sulfur dioxide concentrations in the upper atmosphere have plummeted by a factor of 10. Then surged back unpredictably, as if some invisible hand were turning a cosmic faucet on and off. On Earth, such fluctuations would scream volcanoes, but on Venus, where nothing is simple, the truth might be far stranger. Picture this: high above the surface, sunlight tears apart sulfuric acid molecules, releasing sulfur dioxide gas into the air. Over time, these molecules should slowly sink, pulled down by gravity until they vanish from the upper atmosphere entirely. Yet Venus's sulfur dioxide doesn't follow the script. It lingers, spikes, and sometimes vanishes overnight. The most obvious explanation is volcanic eruptions, belching fresh sulfur into the skies like a planetary exhaust pipe. Some of the planet's youngest lava flows, spotted by radar, coincide with these sulfur spikes, fueling suspicions that magma might still be churning beneath the surface. But here's where the plot thickens. If volcanoes were the sole culprit, we'd expect sulfur dioxide to rise steadily from the surface, not dance erratically in the clouds. That's led scientists to suspect another player: unknown chemical reactions, hidden in those corrosive, swirling vapors. Venus's atmosphere is a labyrinth of sulfuric acid droplets, irradiated by relentless UV light, creating a playground for bizarre chemistry. Some researchers propose that sulfur compounds might be clumping together into larger particles, temporarily hiding the gas before releasing it back into the air. Others wonder if electric discharges, whether lightning or some exotic plasma interaction, could be splitting and recombining molecules in ways we've never seen. Then there's the wildest possibility of all, atmospheric waves. Venus's super-rotating winds might be sloshing sulfur dioxide around like water in a spinning bucket, concentrating it in some regions while starving others. Imagine a planet-wide tide, lifting sulfur-rich air from the depths to the cloud tops in rhythmic pulses. If true, it would mean the sulfur cycle isn't just about chemistry or volcanoes. It's a dynamic dance between atmosphere and geology, a feedback loop we're only beginning to decode. What makes this mystery so urgent is what it reveals about Venus's heartbeat. If sulfur spikes trace back to eruptions, they're a smoking gun for ongoing volcanic activity. But if the answer lies in unseen chemistry, it forces us to rethink how alien atmospheres evolve under extreme conditions. Every new mission, from orbiters mapping gas distributions to probes sniffing the air, directly brings us closer to cracking the code. Until then, Venus's sulfur cycle remains a riddle wrapped in acid clouds, a reminder that even the most toxic skies can hide the most tantalizing clues. Dotting Venus's scorched plains like enormous stone pancakes frozen mid-flip, these bizarre geological formations, officially called pancake domes, defy every expectation of how volcanoes should look. Unlike the steep sloped cones we're familiar with on Earth, these domes are almost comically flat, stretching up to 15 miles wide but rising only a few hundred feet at their centers. Their edges taper so sharply they look like they've been pressed into the landscape by a cosmic spatula. And here's the kicker, they're found nowhere else in the solar system. Venus didn't just bake a few of these oddities, it's covered in them. Each one a silent challenge to our understanding of how lava behaves under extreme conditions. The conventional explanation points to an exotic recipe of ultra-thick lava. On Earth, runny basaltic lava spreads easily, creating broad shield volcanoes like Mauna Loa. But if lava is sticky enough, packed with silica like toothpaste, it piles up into steeper domes, such as California's Mono Inyo craters. Venus's pancake domes seem to split the difference. Their flat tops suggest lava too viscous to flow far, yet their sheer size implies eruptions of mind-boggling volume. Picture a colossal lava bubble emerging from the ground, oozing outward just enough to slump into that trademark flat shape before cooling into rock. Some domes even show cracked, wrinkly surfaces, like the skin of a pudding left out too long, hinting that the lava might have cooled and contracted strangely in Venus's furnace-like air. But not all scientists are convinced viscosity alone tells the full story. Alternative theories suggest these domes could be the work of foamy, lava gas-charged magma that frothed like a planetary cappuccino as it erupted. In Venus's crushing atmosphere, where surface pressure is 90 times Earth's, gases dissolved in lava would struggle to escape, potentially creating a bubbly, lightweight mixture that spread in these peculiar flattened shapes. Others propose that pancake domes might form when lava interacts with Venus's toxic soil, creating a chemical reaction that alters its flow properties mid-eruption. Imagine pouring syrup onto a griddle dusted with powdered sugar. The moment they meet, the texture changes completely. Then there's the wildest idea of all. What if these domes aren't lava flows at all, but the scars of underground explosions? Some researchers speculate that pockets of volatile gases trapped beneath Venus's surface could have detonated, heaving slabs of crust upward like a soufflé before they collapsed into flat-topped mounds. If true, it would mean these aren't volcanoes in the traditional sense, but the aftermath of geological pressure cookers blowing their lids. The real intrigue lies in what pancake domes reveal about Venus's volcanic personality. Their sheer abundance suggests the planet didn't just erupt, it did so in a style utterly alien to Earth or Mars. Whether they're products of weird lava chemistry, atmospheric pressure, or something even stranger, each dome is a fossilized snapshot of a geological process we've yet to fully unravel. Future missions might finally settle the debate, but for now, these stony flapjacks remain one of Venus's most delicious mysteries, proof that even something as familiar as a volcano can take on bizarre new forms when the universe decides to break the mold. Venus doesn't just have winds, it has atmospheric whiplash. At the cloud tops, hurricanes rage at speeds topping 200 miles per hour, fast enough to circle the planet in just 4 Earth days. But descend toward the surface, and this frenzy grinds to a crawl, with winds slowing to a sluggish breeze you could outwalk. This dramatic shift isn't just unusual, it's a direct challenge to every atmospheric model scientists have built, proving Venus still holds secrets about how air moves across alien worlds. The contradiction lies in the sheer abruptness of the change. On Earth, wind speeds taper off gradually with altitude, following predictable patterns shaped by temperature and pressure. Venus, though, flips the script. Its upper atmosphere screams along at supersonic velocities, driven by the planet's super-rotation, yet just 30 miles below, those same winds weaken to a mere 5 miles per hour near the surface. It's like jumping from a jet stream into a stagnant swamp, with no clear explanation for where all that energy vanishes. One theory blames the planet's crushing atmospheric pressure. Near the ground, the air is so dense 90 times heavier than Earth's that it acts like an invisible sludge, sapping momentum from the winds through sheer friction. Picture trying to sprint through waist-deep water. No matter how hard you push, the resistance drags you back. But here's the catch. Computer models accounting for this drag still can't replicate the suddenness of the wind's decay. The math insists the transition should be smoother, not the atmospheric brick wall we observe. Another clue might lie in Venus's bizarre temperature inversion. While the surface bakes at nearly 900 degrees Fahrenheit, the lowest layer of the atmosphere actually cools slightly before heating up again higher aloft. This thermal dip could create a kind of atmospheric traffic jam where sinking cold air collides with rising hot air, disrupting wind patterns in ways we don't fully understand. Some researchers speculate this inversion zone acts like a baffle in a pipe, scattering the momentum of the winds before it ever reaches the ground. Then there's the wild card of topography. Venus's rugged highlands and vast plains might be stirring the lower atmosphere like spoons in syrup, creating turbulence that bleeds off energy. Radar maps show strange, wind-scoured features near mountain ranges, hinting at localized gusts defying the global calm. Yet with no direct measurements from the surface, it's impossible to say how much terrain really influences the sluggish winds, or if it's just another piece of the puzzle. The implications stretch far beyond Venus. If we can't explain why winds die so abruptly here, how can we trust our models for exoplanets with similar thick, super-rotating atmospheres? Every failed simulation forces scientists back to the drawing board, questioning whether they've missed some fundamental law of fluid dynamics. Until we land probes capable of weathering Venus's surface for more than a few hours, this atmospheric enigma will keep resisting explanation, a reminder that even the most hellish planets have subtle, invisible forces we're only beginning to sense. At the towering peaks of Venus's mountains, something impossible glimmers, a mysterious, metallic snow that shouldn't exist in a world hot enough to melt lead. Radar scans reveal these high-altitude regions shining brighter than the surrounding terrain, as if dusted with a layer of reflective frost. But this isn't water ice or even dry ice like on Mars. The best guess, compounds like lead sulfide or bismuth telluride, heavy metals that might condense out of Venus's scorching atmosphere like a toxic metallic mist. Picture a mountaintop where the snow isn't cold and fluffy, but searing hot and deadly, a shimmering, otherworldly frost forged in a chemistry lab from hell. How does this bizarre phenomenon happen? It starts with Venus's runaway greenhouse atmosphere, packed with sulfur and metal vapors wafting up from volcanic activity below. As these gases rise to higher, cooler elevations, relatively speaking, since cool here still means several hundred degrees, they might condense into microscopic metallic crystals, settling onto mountaintops like a fine, radioactive glitter. The process mirrors how snow forms on Earth, with water vapor freezing into flakes, but swaps water for vaporized metals and freezing for a grotesque parody of precipitation. The real puzzle isn't just what the snow is made of, but why it sticks around at all. Venus's lower atmosphere is a constant fury of corrosive gases and hurricane-force winds, yet these metallic deposits cling stubbornly to the highest peaks, resisting erosion like some kind of alien armor. One theory suggests the snow might be constantly replenished by volcanic outgassing, with fresh metal vapors cycling through the atmosphere in an endless loop. Another proposes that Venus's highland temperatures hit a Goldilocks zone just right for these compounds to condense, but not so hot that they vaporize again. Then there's the eerie similarity to Earth's own frost lines, the altitudes above which water freezes into permanent snowcaps. Venus's version twists this concept into something sinister, a condensation line where metals crystallize out of the sky, painting the mountains in a lethal sheen. Future missions could finally nail down the snow's composition, but for now, it remains one of the planet's most poetic contradictions. A beautiful, deadly reminder that even in the most hostile environments, nature finds a way to write its own rules. Venus doesn't just spin slowly, it spins backward, turning clockwise, while nearly every other planet in the solar system, including Earth, rotates counterclockwise. This bizarre retrograde motion, combined with its extreme axial tilt of 177 degrees, means Venus is essentially upside down, with its north pole pointing where most planets' south poles should be. If you could stand on its surface, the sun would rise in the west and set in the east, defying every cosmic norm we take for granted. But how did our planetary neighbor end up spinning like a cosmic rebel? And what kind of violence could have knocked it off kilter so dramatically? The leading theory points to a planetary scale collision, an ancient impact so colossal it literally flipped Venus on its head. Picture a protoplanet, perhaps the size of Mars, slamming into young Venus with enough force to reverse its spin or tip its axis entirely. Such a catastrophe wouldn't be unprecedented. Earth's own moon is thought to have formed from debris after a similar impact. But here's where things get messy. If Venus was struck, why don't we see more evidence, like a moon or leftover debris? Earth's collision left behind the moon as a permanent witness, but Venus orbits alone, its violent past seemingly erased. Some researchers argue the planet's thick atmosphere and volcanic resurfacing may have buried the scars, leaving only its backward spin as a cryptic clue. Not everyone's convinced by the impact hypothesis, though. Alternative explanations suggest gravitational tugs from the Sun, combined with tidal forces from Venus's once thick atmosphere, could have gradually slowed and reversed its rotation over billions of years. Think of it like a cosmic game of tug-of-war. As the Sun's gravity pulled on Venus's dense atmosphere, the resulting friction might have acted like a brake, slowing the planet's spin until it eventually reversed direction. It's a subtle process, but over astronomical timescales, even small forces can add up to dramatic changes. Then there's the wild card of resonance. Some models propose Venus's rotation could have been influenced by gravitational interactions with Earth itself, locking it into a strange orbital dance that altered its spin. This idea stems from the curious fact that Venus and Earth's orbits nearly sync up in a rhythmic pattern, with Venus completing almost exactly 13 rotations for every 8 Earth years. Coincidence, maybe, but celestial mechanics rarely leave things to chance. What makes this mystery so thorny is that Venus's spin and tilt might not even share the same origin story. The axial tilt could stem from an ancient impact, while the retrograde rotation might be the work of atmospheric tides, leaving scientists to untangle two intertwined puzzles. Every new mission to Venus brings fresh data, but until we peer deeper into its hidden interior or uncover ancient impact debris trapped in its orbit, the planet's backward spin remains one of its most defiant riddles, a reminder that even the simplest motions in our solar system can hide violent, chaotic histories. Beneath Venus's suffocating clouds and scorching plains, clues point to an unimaginable past, a time when this inferno might have glistened with liquid water. Climate models and geological evidence paint a portrait of a world that could have resembled early Earth, with vast shallow oceans lapping against volcanic shores under a hazy orange sky. The theory rests on more than just speculation. Venus's current deuterium to hydrogen ratio, a chemical fingerprint left behind when water escapes into space, suggests it once harbored enough water to cover its surface in a global ocean at least 10 feet deep. That's comparable to all of Earth's freshwater reserves combined, vanished into the void over billions of years. What's staggering isn't just that Venus had water, but how long it might have kept it. Recent simulations suggest the planet could have maintained temperate conditions for 2 to 3 billion years, half the solar system's history, before succumbing to a runaway greenhouse effect. Picture a world where balmy seas, warmed by a young sun 20% dimmer than today, lapped against continents rich with volcanic soil. With an atmosphere slightly thicker than Earth's but not yet choked by carbon dioxide, Venus might have been a pale blue dot long before Earth became one. The tipping point likely came from the sun itself. As our star gradually brightened over eons, Venus's proximity placed it squarely in the crosshairs of rising solar radiation. Water vapor, a potent greenhouse gas, began accumulating in the atmosphere, trapping heat that evaporated more oceans, which trapped more heat, a vicious cycle spiraling out of control. Unlike Earth, where oceans regulate climate by absorbing carbon dioxide, Venus lacked plate tectonics to recycle its atmospheric gases. Carbon built up relentlessly, turning the air into a suffocating blanket. Yet the mystery isn't just how Venus lost its water, but why Earth didn't share the same fate. Both planets started with similar ingredients, but Earth's faster rotation may have been its salvation. Spinning quicker generated a protective magnetic field, shielding our atmosphere from solar wind erosion. Venus, turning at a snail's pace, couldn't muster the same defense. Its water molecules, split by sunlight into hydrogen and oxygen, saw their hydrogen atoms stripped away by charged solar particles like leaves in a cosmic hurricane. Some simulations propose an even darker twist. Venus's oceans might have boiled away in a geological instant. If volcanic eruptions pumped enough greenhouse gases into the air within a few million years, the planet could have crossed a threshold where evaporation outpaced cloud formation, leaving no reflective cover to bounce sunlight back into space. The result, a sudden, irreversible bake-off, turning a habitable world into a pressure cooker in what amounts to a blink in planetary time. The haunting implication is that Venus wasn't always a warning, it was a possibility. Studying its fossil climates isn't just about solving a planetary cold case. It's a window into how delicate the equilibrium of a living world truly is. Every probe we send into those toxic clouds isn't just exploring another planet. It's reading the diary of Earth's alter ego, a cautionary tale written in lost oceans and runaway chemistry. Among the swirling chaos of Venus's atmosphere, one feature stands out with eerie precision: a colossal Y-shaped cloud structure, so vast it could stretch from New York to Los Angeles. This atmospheric anomaly isn't some fleeting weather pattern. It's a near-permanent fixture, persisting for decades with a stability that defies the planet's otherwise turbulent skies. Like a ghostly signature etched across the clouds, this formation reappears in the same spot every few days, as if Venus itself is stamping its identity into the heavens. The secret to this Y-shaped marvel lies in a phenomenon called an atmospheric wave. a planetary scale ripple generated by Venus's geography. As super-rotating winds slam into massive surface features like Aphrodite Terra, a continent-sized highland, the airflow gets wrenched upward, creating a standing wave that propagates through the atmosphere. Picture ocean waves crashing against a cliff, but instead of water, it's a 300-mile-per-hour river of gas colliding with a mountain range. The result: a shock wave that ripples outward, bending and stretching into that distinctive Y shape as it interacts with Venus's rapid winds and corrosive chemistry. What's baffling isn't just the formation, it's the endurance. On Earth, such atmospheric waves dissipate quickly, torn apart by shifting weather systems. Venus's version, however, locks into place like a cosmic feedback loop. The planet's slow rotation and lack of seasonal changes create a static environment where the wave can regenerate itself indefinitely. Each time the super-rotating winds complete another lap of the planet, they encounter the same topographic obstacles, reinforcing the pattern like a needle stuck on a record. Then there's the wild card role of solar heating. As sunlight fries Venus's day side, it fuels convection currents that rise and twist, adding energy to the wave like a perpetual motion machine. Some researchers suspect the Y shape acts as an atmospheric drain, funneling energy from the equator toward the poles and helping sustain the planet's supersonic winds. It's a delicate balance, one that could unravel if Venus's topography or atmospheric chemistry shifted even slightly. The Y-shaped discontinuity isn't just a curiosity, it's a masterclass in celestial fluid dynamics. No other planet we've observed exhibits such a geometrically precise and enduring atmospheric tattoo. Future missions might finally decode why this pattern, out of all possible shapes, became Venus's calling card. But for now, it remains a mesmerizing example of how chaos can birth order, even in the most hostile corners of the cosmos. Venus doesn't just hide its geological secrets, it guards them behind an impenetrable fortress of crushing pressure and scorching heat, making the search for Venusians one of the most frustrating detective stories in planetary science. Unlike Earth, where networks of seismometers reveal the planet's inner rumblings, Venus's hellish surface destroys delicate instruments within hours. So how do you listen for quakes on a world where the very air is a corrosive, lead-melting weapon? Scientists have had to get creative, turning the atmosphere itself into a giant listening device. One audacious approach involves tracking atmospheric shock waves. Just as earthquakes send ripples through Earth's crust, Venusians should theoretically generate pressure waves in the planet's thick, soupy air. The European Space Agency's Venus Express orbiter attempted this in 2012, scanning for infrared signatures of such disturbances. The idea was simple. If the ground shakes, it should jostle the atmosphere, creating detectable perturbations in temperature or gas density. But Venus's turbulent weather and super-rotating winds create so much noise that isolating seismic signals is like trying to hear a whisper in a hurricane. Then there's the hope of spotting surface changes from orbit. NASA's Magellan mission in the 1990s mapped Venus's terrain with radar, and future missions like Veritas aim to compare new images with those decades-old snapshots. The goal: to catch fresh fractures or landslides that might betray recent quakes. It's a long shot. Venus's thick atmosphere wears down surface features slowly, and without precise measurements, distinguishing between a million-year-old cliff collapse and a yesterday's quake is nearly impossible. The stakes couldn't be higher. Earth's tectonic activity is fueled by a churning mantle and molten core, but Venus's lack of plate tectonics suggests its interior operates on entirely different rules. Does its crust fracture in sporadic planet-wide spasms? Is magma still oozing up through dormant veins, cracking the surface like a drying riverbed? Or is Venus's interior so stagnant that it barely shudders at all? The absence of data leaves us guessing whether the planet is geologically dead, dormant, or just biding its time. Perhaps the most ingenious proposal involves hunting for quakes from space using lightning. Some theories suggest seismic activity could trigger electrical discharges in Venus's clouds, creating lightning bursts that orbiters could detect. It's a cosmic game of telephone where rumbles in the rock become crackles in the sky. But with the planet's lightning itself still under debate, are those radio bursts really bolts or just atmospheric static? This method remains a tantalizing maybe. What makes this mystery so maddening is that Venus's interior could rewrite planetary science. Earth's geophysical playbook assumes active tectonics and a dynamic core, but if Venus proves those aren't universal requirements, it forces us to reconsider how rocky worlds evolve. Every failed workaround, every indirect measurement that comes up empty, underscores the same humbling truth. Venus, the planet next door, still keeps its heartbeat locked away, leaving us to press our ears against the clouds and wonder. While the highland snow caps Venus's mountains with a ghostly metallic sheen, the planet's lowlands might be hiding an even stranger phenomenon: rivers of frost forged from metals so volatile they'd vanish instantly on Earth. Imagine basins where the air itself condenses into a shimmering, poisonous glaze of cadmium or lead, coating the rocks like a toxic morning dew. This isn't science fiction. It's a chilling possibility raised by Venus's extreme chemistry, where temperatures and pressures conspire to turn the unthinkable into reality. The logic is as brutal as the environment. In Venus's lower elevations, the atmosphere presses down with 90 times the force of Earth's sea level, creating conditions where gases that would normally stay airborne elsewhere behave in bizarre ways. Here, trace metals vaporized by volcanic activity or baked out of surface minerals could reach saturation points, forcing them to condense directly onto the ground like frost on a winter window, except instead of water, it's a metallic mist settling in the dead of night. Picture a valley where the frost isn't just cold but lethally heavy, a condensation of elements that would be gaseous almost anywhere else in the solar system. But how does this metallic frost defy evaporation under Venus's scorching heat? The answer lies in a perverse twist of phase diagrams, the charts scientists used to predict how materials behave under different temperatures and pressures. At Venus's surface pressure, the boiling points of metals like cadmium and lead skyrocket, allowing them to exist as liquids or even solids where they'd normally be vapors. Add the planet's relentless volcanic outgassing, which could replenish these metals faster than they vaporize, and you've got a recipe for surreal, temporary frosts forming in the deepest basins like a cruel mockery of Earth's water cycle. The real enigma isn't just the frost's existence, it's the fleeting, almost ghostly nature of it. Unlike the highland snow, which lingers thanks to cooler altitudes, lowland frost would exist in a constant battle between condensation and evaporation, appearing and vanishing with slight shifts in temperature or atmospheric currents. Some models suggest these deposits might only last hours before dissolving back into the toxic air, leaving no trace behind. That makes them nearly impossible to detect with current technology, like trying to photograph a shadow that only forms at midnight. Yet the implications are staggering. If confirmed, metallic frost would reveal a Venus even more chemically dynamic than we imagined, a world where the very air crystallizes into poison under the right conditions. Future missions equipped with spectrometers tuned to these exotic compounds might finally catch this phenomenon in the act, but for now, it remains one of the planet's most haunting hypotheticals. A reminder that beyond the sulfuric clouds and lava plains, Venus still holds secrets written in elements we're only beginning to decode. Venus's ionosphere hides a bizarre secret massive, gaping holes where charged particles vanish into the void, creating cosmic portholes for solar wind to blast straight through. These enigmatic voids, some stretching thousands of miles wide, aren't just atmospheric blemishes. They're evidence of a deeper magnetic mystery wrapped in the planet's toxic shroud. Normally, an ionosphere acts like a shield, buzzing with electrically charged particles that deflect solar radiation. But Venus's version, already crippled by the lack of a global magnetic field, sometimes develops cracks so vast they expose the lower atmosphere to the sun's full fury. The most dramatic of these holes appear near the magnetic poles, regions where Venus's weak, patchy magnetic fields twist into rope-like structures called flux ropes. These tangled knots of magnetism, spotted by missions like ESA's Venus Express, seem to funnel solar wind particles down toward the surface like a cosmic drainpipe. The process is eerily similar to what happens at Earth's poles during auroras, except on Venus, there's no protective magnetosphere to soften the blow. Instead, the solar wind might be stripping away already scarce atmospheric gases, accelerating the planet's slow-motion suffocation. What's truly puzzling isn't just the hole's existence, it's their inconsistency. Unlike Earth's predictable auroral ovals, Venus's ionospheric gaps appear and vanish without warning, sometimes lingering for days, other times collapsing in hours. Some researchers blame solar storms, arguing that especially violent bursts of charged particles might rip temporary chasms in the ionosphere. Others point to the planet's bizarre, indigenous magnetic fields, localized patches of magnetism generated by the interaction of solar wind with the upper atmosphere. These flickering, unpredictable fields could be carving escape routes for particles, like invisible scalpels slicing through the ionosphere's fabric. Then there's the haunting possibility that these holes are relics of a dying dynamo. Venus's core, though sluggish, might still harbor pockets of molten metal moving just enough to generate patchy magnetic bubbles. If so, the ionospheric gaps could be fleeting glimpses of a once global magnetic field in its death, throws a planetary magnetosphere reduced to ghostly flickers. Every ionospheric tear raises new questions. How much atmosphere is Venus losing through these wounds? Could the influx of solar particles trigger chemical reactions that alter cloud formation or even surface chemistry? With no dedicated mission observing these phenomena up close, the holes remain one of Venus's most urgent riddles, a reminder that even a planet without a magnetic field can still play host to invisible, electrifying dramas. Venus stands eerily alone today, but what if it once had companions, moons that orbited this hostile world before vanishing into cosmic history? The idea isn't as far-fetched as it sounds. Earth's moon was born from a cataclysmic collision, and Mars has two captured asteroids as its tiny satellites. Yet Venus, despite being nearly identical in size to Earth, has nothing circling it but empty space. This absence has fueled theories that the planet wasn't always so solitary, that it may have once had moons, only to lose them in a gravitational tug of war or a violent encounter buried deep in time. One compelling explanation points to the planet's peculiar rotation. Venus spins backward at a glacial pace, a quirk that suggests something massive like a moon could have disrupted its original spin. Here's how it might have played out. If Venus once had a sizable satellite, tidal forces between the planet and its moon would have gradually slowed Venus's rotation while pushing the moon outward, much like Earth's moon is slowly drifting away from us. But unlike Earth, where the process is gradual, Venus's thick atmosphere and extreme solar tides could have accelerated the moon's escape. Over billions of years, the moon might have spiraled so far out that it broke free of Venus's gravity entirely, becoming just another wanderer in the solar system. Then there's the collision hypothesis. Imagine a proto-moon, perhaps formed alongside Venus in the chaotic early solar system, only to be shattered by a later asteroid or comet impact. The debris could have either scattered into space or crashed back into Venus, leaving no trace behind. This scenario would explain not just the lack of moons today, but also Venus's oddly young surface resurfaced by lava flows that may have buried the evidence of such an ancient cataclysm. But here's where it gets even stranger. Some simulations suggest Venus might have had multiple moons at different points in its history, each meeting a different fate. One could have escaped, another might have collided with the planet, and a third could have been torn apart by tidal forces, forming a temporary ring system before disintegrating entirely. These theories aren't just speculative, they're backed by orbital mechanics showing how unstable moon systems can be around slowly rotating planets. Without a large stabilizing satellite like Earth's moon, Venus's gravitational environment would have been a chaotic arena where small moons were easily lost or destroyed. The most tantalizing clue comes from Venus's near-resonant orbit with Earth. For every 8 years Earth takes to circle the Sun, Venus completes almost exactly 13 orbits, a rhythmic dance that hints at past gravitational interactions. Could Earth have stolen a moon from Venus during a close encounter billions of years ago? Or might the two planets have exchanged smaller satellites in their youth like celestial trading cards? The math shows it's possible, but with no physical evidence left behind, the case remains wide open. What makes this mystery so captivating is the sheer audacity of its implications. If Venus did have moons, their disappearance would rewrite the planet's entire history, from its rotation to its climate. A large moon could have stabilized Venus's axis, preventing the extreme tilt we see today. It might even have influenced the planet's volcanic activity or atmospheric evolution. Without one, Venus was left to spiral into the chaotic, solitary world we know now, a cautionary tale of how celestial companionship, or the lack of it, can shape a planet's destiny. For now, the missing moons of Venus remain a ghost story written in gravity and orbital mechanics. Until future missions uncover ancient impact scars or gravitational anomalies that hint at lost satellites, we're left to ponder a haunting question. Was Venus once part of a cosmic duo, or has it always been the solar system's lone wolf? Either way, its emptiness speaks volumes about the fragile dances that bind worlds together or tear them apart. Venus has spent decades laughing in the face of every assumption we've thrown at it, a world where rivers of molten metal might flow, where mountains glitter with toxic snow, and where the very air moves faster than the planet beneath it. From its backward spin to the vanishing act of its water, from the phosphine debate to the dragon storm's eternal whirl, each mystery we've explored today proves one thing: Venus isn't just Earth's twisted twin. It's a cosmic rebel, rewriting the rules of planetary science one enigma at a time. And the plot thickens because humanity isn't done probing those acid clouds. NASA DAVINCI mission will plunge a probe straight into Venus's atmosphere, tasting its chemistry like never before, while Veritas will map its surface in razor-sharp detail, hunting for volcanic hotspots and tectonic ghosts. Over in Europe, Envision plans to scan the planet with radar and infrared eyes, teasing apart the secrets of its tesserae and coronae. These missions aren't just about answers, they're about uncovering the questions we haven't even thought to ask yet. So here's the real twist: Venus isn't finished surprising us. Maybe those clouds do hide life. Maybe its volcanoes are still sculpting the landscape right now. Or maybe the next probe will stumble upon a mystery so wild it makes today's list look tame. That's the thrill of exploration. The universe always keeps a few cards up its sleeve. Now it's your turn. Which of Venus's riddles keeps you up at night? The metallic snow, the missing moons, the ashen light glowing in the darkness? Drop your favorite mystery in the comments, and while you're at it, take a fresh look at that bright star in our evening sky. Because after today, you'll never see Venus the same way.